And then write down, okay, number 54. All right, so chapter 35, number 54. All right, so let's go to my screen share. Let's see, maybe I should read this carefully. On your iPhone, G5. Now, it says, I wonder if that's making a difference. Let me try something. Just notice my laptop is hooked to well, you guys probably have the same thing, but my Wi-Fi at home here has a, it has a G5, but it also has the older 2.4.
Mm-hmm.
And I can
the dual band?
Huh?
The dual band they have there?
Yeah, I guess that's the name they call it, dual band. And I just noticed that my laptop is connected to the 5G and my phone is the 2G. But it's the same network, but
yeah, I know 5G. It's a faster speed, but a less steady connection. Whereas the 2.4G, it's not quite as fast, but it's more reliable. Or at least I've dealt with all the internet setup for my family for like the past decade, so that's at least what I remember.
Yeah. Okay. Well, in my experience, has been kind of like that. I have the 5G is faster, but with the 2.4G, I've noticed it extends further out past the walls. When I put my my laptop has a signal detector, and as I walk around the house, if you're close to the Wi-Fi, the 5G is great because it's fast, but you get a couple walls and it sucks. So maybe we're talking about the same thing, reliability and the walls.
Yeah. One thing I would need to look into it to double check there, but if I'm not mistaken, that actually has to do, I think that actually has to do with like the wavelengths or something of the signals, which might be why one of them is more likely to go through more material. I don't know. If you want to make that a physics question in the future.
No, that's very, everything you said is very true. That's why the different wavelengths have their advantages and different, disadvantages. In general, the higher the frequency, the more data you can put, but if it doesn't penetrate very deeply, that's not good. In fact, the old TV signals are in that 100 megahertz range because they do so well of going through concrete and steel walls and into buildings really well. So, anyways, this will be my experiment for today. Anyways, I'm going to switch so that my phone and laptop are on the same network. But that's where it gets confusing. They're the same network, it's just a different band. So, and it obviously worked. It just kept crashing. But nonetheless, put them both on the 5G and we'll see what happens. If you don't like it, we'll put them both on the 2.4, see what happens.
Awesome.
Experiment a little bit.
Crossing our fingers.
But I did want to see, I'm going to write that down. The little icon that pops up on my laptop is called Air Render. And it's got a little icon, and then every once in a while that thing drops away, and then that's when it freezes. So there's something about it. All right. Anyways, on to your question here. Okay, so let me find the questions again. Here we go. All right, so chapter, and we were in 35, weren't we? Yeah, 35. We were doing, what were we doing? It was a tricky one, wasn't it? I guess it doesn't matter what we were doing. Let me just find 54. Okay, here's 54. All right. So, as sunlight enters the Earth's atmosphere. Oh, and by the way, yeah, right there, Hunter, you had commented earlier on, should I use 1 or 1.0003 for the index? And I have a feeling that I need to distinguish between space with an index of 1 and the atmosphere of 1.0003.
Hmm.
All right. It changes direction due to small differences in the speed of the light in the vacuum in the air. Okay. Yeah. The duration of the optical day is defined as the time interval between the instants when the top of the rising sun is just visible above the horizon and the instant when the top of the sun just disappears. Okay. So that's the optical day. Now, the duration of the geometric day is defined as the time interval between the instant when a mathematically straight line between an observer and the top of the sun just clears the horizon and just below. Oh, okay. Explain which is longer, an optical day or a geometric day. Okay, so it's going to be an optical day. I'll draw a picture here. Find the difference between the two. Ooh, this should be interesting here. Okay. Well, maybe I'll read all of them. Let's see. Find the difference between the two intervals. Model the Earth's atmosphere as a uniform index. There it is, 1.000293. They do a little bit better. And a sharply defined upper boundary, which probably isn't true, at a and depth of 8,614 meters. Assume the observer is at the Earth's equator. So, all right. So the apparent path. Okay. Yeah. This is all really good here. Okay. So this 54, I guess, would look. Let's see if I could say it. Something like this. If this, say, is the Earth itself, okay, and then I have a atmosphere around it, okay, then I would see the light here. And so maybe I'll just draw a radius line out from the center of the Earth where I'm standing. And what I would call the beginning of the optical day, if you will, is when I see the light coming at me. But here's the neat thing is it would have been coming from the sun that is actually below the horizon. It would come up and then bend towards the normal a little bit and then come straight across. So I could actually see the tip of the sun before a geometric day. A geometric day, without the bending of light. So I'll just kind of put a dotted line to represent the atmosphere, but I'm going to say that the atmosphere doesn't affect the light. If I was right here at the equator, the sun would have to get all the way up to here. So the first part of this is which is going to be a little longer. It's going to be the optical day because I'm going to actually see the sun just a fraction before it gets to level, if you will, with the horizon.
Yeah, and the optical day is going to be the one that like an individual would observe, basically, right? Whereas the geometric isn't.
Yeah, and of course now now from your perspective, coming back here, not knowing it actually bent in the upper atmosphere, you would look straight across and you would see the sun, rising right at the horizon. You would say, "Oh, I'm doing a geometric day because I can see the sun right on the horizon."
Mhm.
And of course, it just appears to be on the horizon. In the same way, a more extreme case is if you were looking in a mirror, and you see something in the mirror and you go, "Oh, I see it." I,
Mhm.
I see Bob over there on the other side of the mirror. And if it's a bathroom mirror, you go, "Okay, that must mean Bob's on the other side of that wall. Oh, that means Bob's in the kitchen." Well,
Mhm.
no, Bob's in the bathroom right next to you. It just, you see his reflection. So if you don't
Mhm.
realize the light gets redirected, you just see it as a window, and you go from there.
Okay.
So yeah, you couldn't tell with your eyes only the difference between the optical day and the geometric.
All right, makes sense.
Yeah, but there is some small angle there, and and that's actually really the problem here, is to figure out what that is. What is that small difference? So I would say that the light coming in is this right here. Let me call it theta 1. There's the normal going out. And of course, then it bends right here. Let's call that theta 2. And I would then say that, and here's the Snell's law part of it, that n1 sine theta 1 is equal to n2 sine theta 2. Now, uh, maybe I'll put in my indices first. The light's coming from outer space, so there's a vacuum. It then enters at some angle. That's ultimately what I kind of like to know, because watch this. Here's where it hits the air, 1.0002. What is this? 293. And then sine of theta 2. Okay. Now, the theta 2, and this is kind of like the other problems we were doing before the break, I think I can get from geometry. See, they gave me a little bit of information about the size of the atmosphere. Okay. And I know the radius of the Earth. So if I look, maybe I'll do the triangle in green right here. And I look at this triangle. Sine of theta 2 would be right here, the radius of the Earth over the hypotenuse. And the hypotenuse is the radius plus the height of the atmosphere. So I'm going to just put as another equation from geometry or trigonometry, maybe is a better word there, that the opposite is the radius of the Earth, and the hypotenuse is the radius of the Earth plus, maybe I'll just say h for the height of the atmosphere. So the radius of the Earth, and it wasn't given in the problem, I don't think. Was it given? No. So I got to go to the front cover or Google it.
Yeah, but we can find it in the survey textbook, right?
Yeah, it's in the front cover of the survey textbook. But it's 6.67 million meters. And then down here would be the 6.37 million meters plus the 8,614. By the way, you can. Well, yeah, never mind. I was going to compare it to something else, but I should just then calculate what this is. So let's see. The bottom is 6.37 million plus 806.14. That's the bottom. Why don't I just say 6.37 million meters on the top divided by that last answer. So there's the sine of the angle. Let me go inverse sine. And looks like 87.0 degrees is theta number 2 from the geometry. And of course, now taking that and coming back up here to the physics. So sine theta 1 equals 1.0000293 sine of that angle. In fact, maybe I'll just go up. Before I did the inverse sine, I actually had the sine of it. So that's the sine of the angle. I guess I didn't have to go inverse sine. But let me multiply it by 1.000293. And then do inverse sine of that one. And it looks like the angle coming in is 87.36. Actually, let me go extra decimal since these aren't much. So theta 2 is 87.02 and theta 1 is 87.36. So again, there's some bending, not much, and that's kind of our guess. Our index barely changed. I mean, that's why we had said so often we use just an index of 1 for error because it barely changes its speed, so it barely bends. But some problems, that's what it's after, and that's what this is saying. It barely bends, but it does bend, and instead of being this angle, it changes down to that angle. So there is a slight bending to it. Okay, but coming back to my picture, then this is the angle I'm kind of curious about. This light would have gone straight in. So that's what a geometric day would have been. And if it would have gone straight in, that would have been the 87.02 degrees. But instead, the angle is 87.36. So what I'm getting at is if we subtract these two, if we take theta 1 and subtract theta 2, we get 0.34 degrees. So again, not much of a change, about a third of a degree. But you actually would see the sun rising a third of a degree sooner than otherwise. There's our first freeze. Okay.
I mean, hey, we made it like 20 minutes this time.
Yeah, maybe that's a better sign. All right. But again, so number wise, the Earth, you know, trying to put this in words, the as the Earth is rotating, so the Earth is rotating like this, and you actually see it a little earlier than you would have seen it. The Earth would have to rotate another 1/3 of a degree, basically, before you would have seen it without this effect of refraction. And so we see it a little bit early, 1/3 of a degree. So now the question is, okay, 1/3 a degree is how much time? Because, the question was asking, how much earlier or sorry, it was saying how much longer is the day. And so the day would be earlier by a 1/3 of a degree of rotation. All right. So I'm gonna do this. I'm gonna think of it in terms of fractions. I know that in a 24-hour period, the Earth rotates one full revolution, 365 degrees. So the amount of time is actually 0.34 of a degree out of a full 360. And so I'm going to use the fraction of the circle I want, 1/3 of a degree compared to the whole circle out of the 24 hours. So that's how much earlier sunrise would be without this bending of light. So 0.34 divided by 360. So that's the fraction of 24 hours. So that's how many hours. So if I multiply it by 60, that's how many minutes. And if I multiply that by another 60, that's how many seconds. So it looks like we see it because of the atmosphere. Well, we see sunrise 81.6 seconds early. Okay. Of course, that's at the equator, so that's not really what we see. Okay, but that's using the radius of the equator. For us to be a little different. But let me also point out that the same thing would happen during sunset. You would see it set a little bit later. So I need to double that. And we're going to see light. Because of the atmosphere, we see the sun an actual 163 seconds longer than we would have without an atmosphere. So we had no atmosphere. Oh, that was a cool one. Oh, nice.
Oh, that's really cool.
All right. Well, looks like you guys can control the discussion here, what we want to do. Nothing in the chat.
I think there was a part B to it asking to find, asking to find the time difference between the two intervals, and that's what we just did. Right. Yeah, it is. Sorry.
Yeah, no. Yeah, so the first part was just explain, which is longer.
Mm-hmm.
Yeah.
And why. Yeah, and we kind of went over that already.
And why. So I kind of did that one first and then went to the numbers.
I think Johnny just put something in the chat.
All right. Sure can. Let's see. Number 35, number 60. Okay. So 35, number 60, and at 3:30. Ooh. I wonder when I hit record. I have to write the time down. I'm going to put 3:02. Been a couple minutes. That's probably what I did. All right. Or did I hit record? Yeah, I did. Okay, it's recording. All right, let's try. And I'm just going to not even give myself another piece of paper. Do that. All right, so chapter 35, number 60. Sounds like more wonderful geometry and Snell's law. 60. Ooh, looks like we got a sphere here or cylinder or something. So a transparent cylinder. So we got a cylinder. Looks like we're looking edge on a cylinder. A radius of 2 meters. Has a mirrored surface on its right half, as shown in figure 60. A light ray travels in the air, incidented from the left-hand side of the cylinder. The incidented light ray and the exiting light ray are parallel, and they are d 2 meters apart. Determine the index of refraction. Okay, so here is the cross section of that cylinder. And they've got the lights coming in. And if I draw a normal, and let me point out when we did that other problem with a quarter of a circle, probably an important thing to know is that the normal is a radius line and it goes right towards the center. So usually when we're dealing with circular geometries, that's part of it. So this would bend towards the normal. And in this case, it's the right-hand side, the arrowhead here, bounces off. And again, let me draw a normal. And this time we bend away from the normal. And also, I'll try to draw it parallel. They said that these incoming and outgoing beam are 2 meters apart and parallel to each other. Okay. Now, I have a feeling this is going to come into play. There's some geometry here. Well, let me start with the physics. But again, I think the harder part maybe is more geometry than it is, or geometry / trigonometry than it is physics. But let me do this. Let me call this angle coming in theta 1. And then this angle here, theta 2. Now, there's a lot of symmetry going on here. So maybe I'll do a little proof here in a moment, but if you look at this angle over here on this far side, I'm hoping you see that this angle is a theta 2 also. That's because this green triangle is an isosceles triangle, because from here out is a radius and here out is a radius. And in case you forgot from your geometry, the an isosceles triangle where the two lengths are the same result in the two angles at the base being the same. And so this is where I'm going to use the law of reflection and then say that would be theta 2 in there because it comes and bounces off of a mirror, which then this triangle down below, which maybe I'll do in purple, but I don't know if it'll stand out too much from the red, but it too would be an isosceles triangle such that this angle here would be a theta 2. And so as it bends away from the normal, and in order to be parallel, this must come back to theta 1. And what I started to say is, I don't know if you can see the symmetry in here, but if you draw a horizontal line down the middle, the top half looks just like the bottom half. So applying Snell's law when it goes into the glass is really the same as applying Snell's law when it goes out of the glass. There's no new information. So I'm gonna write down Snell's law just one time. Oh, hey, hang on, guys. I guess I'll go Thursday. Yeah. Thank you. Yeah, I'm trying to set up my second vaccine shot. So I'm actually not due for a while. I think it's only been 2 weeks. I got another 2 weeks, but all the appointments are full. So I'm like, no. Anyway, so we're trying not to miss my second one. All right.
Of course not. That's awesome.
Yeah. So, all right. Where was I? Oh, yeah. So what I was trying to say is I'm going to apply Snell's law, and I'm only going to do it once. I know that in many of the other problems, I would do it twice because it gave me useful information. But in this case, the fact that they tell me it's parallel is the same information as applying Snell's law twice. So that's why once they tell me it's parallel, the second Snell's law doesn't give me any more information. All right, so I'm going to apply this coming in here. Let's see. Did they say we were in air? The radius is 2 meters. Mirrored surface on the right. The light ray is traveling in air. Okay. So on this first surface coming in, if I go N1, I would call it 1, and then I would have sine theta 1. Okay. Then I would go into here, which would be N of the material. And then I would have sine of theta 2. Now, here we go. Watch this little geometric trick. And you can kind of see it. I did it earlier. Remember this theta 1 is the same as down here, this theta 1. And the reason that is helpful, maybe I'll draw the bigger green triangle again. We did something like this on another problem. So if this is theta 2 and outside is theta 1, and then we argued that over here would also be a theta 2. This theta 1 is what's called an external angle. Okay. And I didn't mention this, but I kind of proved it. If you take an external angle, theta 1 is actually equal to the sum of the two internal angles. Now, the way I did it before is I just took this angle and said that angle would be 180 minus theta 1. And then I said if you add all three of these angles, so in this case it would be theta 2 plus another theta 2 plus 180 minus theta 1 has to equal 180. Then I canceled off the 180s. And then I said theta 1 would have to equal the two angles. Now, in the problem we did, the two internal angles I called 2 and 3. So we said theta 1 was equal to 2 plus 3. They weren't equal to each other. Oh, I think that was that long one right before the break. Yeah. But in this case, and so I don't know why I didn't say it. I guess partly because I was focused on the problem, but also I don't know if it's worth memorizing because you can prove it each time. But one thing to remember nice from geometry is that this what I just did is really taking what we would call the supplemental angle, and all three angles add up to 180. If you put those two pieces together, you can prove that an external angle is equal to the sum of the two internal angles. Now, I didn't want to say that in the last one or this one just because that's one of those proofs that although it's true, you don't use it very often and you may not remember it. So I don't want to say, hey, it's so obvious, you should remember that the external angle is equal to the sum of the two internal ones. But it is. And so I could now say then, especially since the two are equal, that theta 1 is twice theta 2. Now that's really what I'm getting at. Okay. All right. So now, and depending on which way we want to substitute this in, I'll take the sine, and for theta 1, I'll put 2 theta 2 equals to n over the sine of theta 2. Oh. All right. Now, I question if that was wise, because as I look back at my geometry here, it's pretty easy to get theta 1. Remember that they said these two parallel beams right here were 2 meters apart. So that means from the center up is 1 meter. If I put that 1 meter right here, remembering that this is theta 1, I could then write sine of theta 1. And so it would be opposite. So that's 1 meter over the radius. Oh, and I think the radius is 1 meter, isn't it? No, radius is 2 meters. 2 meters.
It says the diameter is 2 meters, right? Oh no, sorry. D is for the distance.
Yeah, that's what I was thinking. Maybe I read it that way because I was, for some reason, or maybe it's that D confused me. But anyways, for some reason I had a double look at it because I thought I was thinking the diameter was 2 meters. Mm-hmm. So maybe that's the way I first read it. But anyways, as I look closer at it, its radius is 2 meters. Anyways, that will allow me to get both theta 1 and theta 2. So using the inverse sine function, so inverse sine of 1 over 2. Oh, I should know that. 30 degrees. That's an obvious one. All right. So that means we've got 15 degrees for theta 2. Which means over here, we can go sine of 30 degrees divided by sine of 15 degrees gives me the N. So sine of 30 degrees is 1/2. And if I divide that by the sine of 15, I get N equaling 1.93. Yay! And
Isn't that like glass or something?
no, glass is much lower than that. Glass is like regular glass. Silicon glass is about 1.5. You get to the flint or the lead glass, you get 1.6, 1.7. 1.9 is pretty high. Yeah. Well, in fact, let me scroll down here. First of all, check the answer. Yeah, 1.93. But if I flip over to the textbook, yeah, that's textbook. I don't see anything that really matches. All right, well, then set me up on Friday.
So he can do the first, or he can just take a sick day and come on Friday? Mike Young?
Yeah, let's go Friday.
Okay, then I
Oh. And bummer. They can only set me up appointment on Friday, so we'll have to figure out something about the Zooms, but that's another story.
Hey, safety first.
So we'll have to do a makeup Zoom or something for it. All right. And we probably could still get half of it in depending what time they're setting me up for a time. All right. Oh, but I was kind of curious. I don't have the textbook open. The index is, let me open up my, well, not real crucial. I should go back to the questions, but I am kind of curious. That's not a index that I normally think of. Only thing that starts to get that high I can think of is like diamond, but diamond's even higher. It's like 2.4. Yeah. Yeah, see, because our little chart goes diamond at 2.4, cubic zirconium 2.2, and then the next biggest one is probably the flint glass at 1.66. So anyways, but I'm sure there's some material that is manufactured to get that number. But,
Without diving into it too far, I'm just curious, why is flint glass more have a higher end than just regular glass there?
Yeah, you'll notice that they never really, for this intro to optics, really explained why we have a index. And the analogy I like to give is this, and I'll maybe draw a picture. Is we talk about the light going slower, but that statement is a little misleading. Let's say I have a piece of material and the light comes in. What'll happen is it will interact with the atom here. And so you might say it kind of pauses with an interaction and then gets re-radiated. Then it goes to another atom, and it might not be the next one. It may travel many atoms before it interacts again. And then there's kind of a delay. And so I like to use kind of a silly example that if I was walking through, say, a cafeteria, I might if I didn't stop, if I didn't talk to anybody, and just walk straight through the cafeteria, I would travel through at my walking speed. Let's call that c for the speed of light. Okay. But if I get to the first table and I recognize somebody, and I stop and say, "Hi, how you doing? Oh, having lunch. What are you eating? Okay, have a good day. Bye." Then, even though I'm still walking at my walking speed, and maybe I do that twice before I get all the way across the cafeteria, if all you measure is me going in and me coming out of the cafeteria, you're going to say, "Oh, you walked slower through the cafeteria." Well, I didn't really walk slow. I paused because I had some interaction. And that's a better way to describe what's going on with the light. The light kind of pauses and has an interaction and gets re-radiated. Now,
Okay.
so now it boils down to this interaction, and that's where different materials will interact differently, resulting in a different end.
Okay, that makes sense. So it has I'm guessing it has a lot to do with the density of atoms in the material, but also I'm guessing like rigidity of the material too,
Well,
like how well it can transfer from one atom to the next in it.
yeah, I'd be careful with the word rigidity because we usually associate that with the material strength, and that's not really what's there. But it really is how much it interacts. And there's two big factors. One of them, as you said, is the density of it. So in general, because one of the factors is density, you'll see that light travels, the fastest in a vacuum where it can't interact at all. Then when you get to air, where air has a very low density, it slows down a little bit, but not much. Then when it gets into water, which has a little higher density, it slows down even more than air. When it gets to glass, it slows down even more. Yeah, so one of the factors is really density, okay? But it's not just density. Remember, it is what the interaction is. And again, using my example, if light was, my analogy of me walking through the cafeteria, if I was being delayed as I go through the cafeteria, one factor would be how many tables, so the density of the tables. But the other factor would who would be at that table. Because there are some people at the table where I would stop and interact for a long time. There's other people at the table that, I just say, "Hi, good to see you, and gotta go." Just, because maybe I just socially don't like them for whatever reason. No, that's not true. I like everybody. Okay. So, but you get what I'm saying. Is you know them better, you have more in common. Maybe that analogy is not very good. Light doesn't have friends and enemies and people they like to talk to and people they don't like to talk to. But what I'm getting at is there is a interaction factor, and that tends to be really dominant. And so if you take a piece of glass, all the glasses, silicon glass, crown glass, Pyrex glass, flint glass, all those glasses have roughly the same density. So now the difference between those glasses would be how much they interact. Flint glass is got it starts with flint and you heat it up until it becomes glass. And I'm not real sure what flint is, but it's different than just plain silicon. And silicon glass and flint glass aren't too much different, but crown glass is and lead glass is. Anyways, and so that's what it boils down to. So,
okay.
And how much they interact.
At the sake of, I actually, if someone else has a question, I don't want to take up more time, but I actually just have a couple more conceptual questions about that.
Sure.
So when you're thinking about, we're dealing with in this section, we're dealing with the visible light spectrum and stuff like that. And so the objects we're working with, they're transparent in the visible light spectrum. Are there like, do we have like other things in like regular life that are just transparent to other like types of like EM radiation, or?
Yeah. In fact, that was the start of our conversation about the Wi-Fi. So um, this interaction that I was talking about, and again, maybe if I keep going along this interaction, so I'm walking through a cafeteria, and I'm the light, and the people at the table are the atoms. I'm slowed down on average. And again, let me emphasize, not between table and table. Between table to table, I'm still walking at my walking speed. But I stop and I interact, and how much interaction I do is a combination of the density of the tables and what is at the table. So what atoms am I interacting with? But it can also go a little further than that, because whatever's at the table could absorb me. Let's say that there was, somebody I hadn't seen since the start of the pandemic. We've both been inoculated, and I'm walking through the cafeteria. I might just downright stop and say, "Wow, we haven't had lunch in over a year." I'm just going to pull up a chair and I'm just going to sit right down, and I never re-radiate. I'm completely absorbed. So there are, some atoms that then interact very strongly with some wavelengths. And
that actually makes sense. We do spectrography in chemistry, right? For that.
Pardon me?
We use like spectrographs in chemistry and stuff like that to do that, right?
Right. And so you can tell what the material is by how much it interacts. So what we would call a transparent window, like glass, and there's different kinds of glasses, but the whole reason it's transparent is it does not interact with visible light. It lets it go through. Sure, it slows it down. There is a little interaction, but it doesn't absorb it. So it has a transparency to it. Now, as you point out, that may not be true in other parts of the electromagnetic spectrum. So like infrared. So if I put a piece of glass between me and a fireplace, I will block that infrared. And without the glass there, I put my hands up and go, "Oh, that's cozy warm." I put the glass there, and I don't feel that anymore, and it gets absorbed. And so now the glass starts to get warm, but the infrared doesn't get to me. So even though I'm saying the glass is transparent, I need to be a little more specific. It's transparent in the visible range.
Okay.
X-rays are exactly that. Human bodies in the visible light, we say they're not transparent. I can't look at you and see your bone structure. But X-rays are transparent to soft tissues. They go right through soft tissue. They do get absorbed by hard tissues. So all you see with an X-ray is hard stuff.
Okay. That's actually really cool. So like you could even think about it theoretically. It's like, hey, concrete might actually be transparent in certain ranges of the spectrum that we deal with. It just isn't in the visible light.
Right. And concrete is pretty transparent at 100 megahertz. So if I want to pick up a radio station inside a building that is made out of concrete and steel, it's good to put the frequency around 100 megahertz. And so that's the whole idea of the FM radio band when it was chosen back whenever it was chosen, probably in the 30s, 1930s sometime, so 90 years ago or something. They recognized that 100 megahertz would be a good number to use for radio communication. Now, the other factor of that is you have to have technology that can go that high. And I think that's the answer why the original AM was lower than that. The AM was set where it was because that was as high as technology could broadcast in its day. And so, okay, this is the best we can do. whether it's the best or not is not really a question. It's just the best we can do. But so concrete's really nice, and so that's kind of my guess about the walls, that the sheetrock is probably pretty transparent at the 2.4 gigahertz, because it works really well through my walls, but the 5 gigahertz does not.
Okay. Huh. All this stuff makes me reminds me a lot about like our physics 122 stuff and how that could possibly interact with. I know in the last section we were going over Maxwell's equations, we went over like cell towers and like radio waves radiating outward and the power that they like emit and stuff. And I'm like, yeah, that's it's in the it's in radio waves instead of visible light waves right there. So it all kind of ties back into one another. And that's just really cool.
Right.
So,
Good. I'm glad you're seeing that. And that's yeah, for those of you, those half of you that have gone through 122, you know that these are just electromagnetic waves. So our optics probably needs to be viewed at, like you are, in a bigger picture, and saying, wow, this is what we're doing is not just true for optics, but it is also true for all of our electromagnetic waves.
yeah. So we could even have lenses as well for thing. We could have lenses for any part of the spectrum too. We could focus X-rays or radio waves by some sort of lens that works with it.
Right, and you probably see it best in the next chapter. You're not quite there, but in chapter 36, we have all these concave mirrors.
Mhm.
And if you look at a satellite dish, that's exactly what a satellite dish is. It's just a concave mirror.
Oh, cool.
Yeah. And of course, it's trying to reflect the satellite waves, which they're around 10 gigahertz, something like that. And they're microwaves. But you could do the same game. You can calculate the focal length and the concavity.
Yeah, it's really cool. Yeah, it just started clicking for me when we were going through all that stuff. I'm like, wait a second, hold on. So, but now that makes it even I already went through the whole chemistry series too. So I'm like, it just really reminds me of like, hey, how is solar energy harvested and stuff like that? And it's like in that one, it's visible light spectrum. I think possibly other stuff too. But anyway, thanks for explaining a lot of that.
Sure. All right. Let's see. What number did we do? Did we just do 60? Oh, we did. Good. And then I don't see another one from you guys, but good questions on a little more than a basic optics. We're getting into some advanced optics here.
Yeah.
And even advanced electromagnetics. You start getting at radio towers and how they radiate the electromagnetics. That's what you said. That's kind of where we ended up and left off, and that's normal, because then now you can go further than that on your next level.
Yeah, looking forward to it. If Johnny doesn't have another one, I have a question in 35 I'd like to go over.
All righty. 35.
It would be number 63 there. In that one, we're trying to determine the N for plastic, or the refraction, and then it's also asking us for a time interval for the light to travel through it, given initial location.
Okay. I'll take your word for it. I got to read this one. This one doesn't sound familiar, but I think I read them all. Reading them last night. Like, okay. See if anything was real tricky. Although usually the tricky ones don't look tricky until I get started. Now, one right before the last break, I looked at that. I go, oh yeah, that's just a bunch of geometry, but that was a good one.
Yeah, then they had you derive an equation and took
a
while.
All right, so let's start this one, but sadly, my phone crashed here. So let me restart. And while that's coming up, I'll click back over to the questions number 63. Oh, okay. Oh yeah. No, well, we'll see what happens here. But again, kind of look at this. I think the physics is probably the easy part. The geometry / trigonometry may not be. Okay, so a light ray enters a rectangular block of plastic at an angle of 45 degrees. So they give a nice little picture here of a rectangular block. And they say the light's coming in, and I'll just put 45 degrees. Now, it emerges as an angle of 76 degrees as shown. Okay, so when it comes in, it's going to bend towards the normal. And as it shoots across the plastic, it's going to bend away from the normal. And so this angle, they say, is 76 degrees. And just for labeling, they call that number 2. And this one over here, angle number 1. Not sure I like those symbols, because we call 1 and 2 the incident and refracted angle. And so these two aren't connected. These are on different surfaces. But all right, that's what they call them. I'll follow that. A says, determine the index of refraction of the plastic. And then B, if the light ray enters the plastic at a point L equaling 50 centimeters. All right, so they say this is L, and they put it at 50 centimeters from the bottom edge. Oh, what time interval is required for the light ray to travel through? All right, looks like 2 real good questions here. But like the other ones we did, why don't I call where it comes in surface number 1 and where it goes out surface number 2. So if I were to write down Snell's law on surface number 1, so there's my picture. But on surface number 1, so let me just write Snell's law as N1 sine theta 1 equals to N2 sine theta 2. And that could be confusing. That's why I didn't like their label for number 2. So I'll tell you what, why don't I just put right in here theta 3. And so quickly, I'll just put in sine of 45 degrees. And I'll put sine of theta 3. I'll put even right above it surface number 1. And did they say we were in air? Enters a block of practice at 45 degrees, emergent as shown in determine the index of refraction. Huh. So maybe I'll just follow their notation and call N2 the plastic one, which is they called N. And they don't say that the plastic is in the air. And last time I just assumed it, and it turned out we didn't need to. It canceled off. So I'm going to leave it as N1, and I have a feeling the same thing's going to happen. And I also think it would be okay to assume it's plastic. I mean, air. But anyways, that would be the equation I get from surface number 1. Now, surface number 2, so when it's exiting the plastic block, and again, I'll just use the notation of Snell's law 1 and 2 real quick, but that can get confusing because the 1 is what it starts in. So if here's surface number 2, it starts here in the plastic, and I'll call that theta number 4. So that right here, this would be just an N because it's the plastic. And then this would be sine of angle number 4. And then it would go into, and whatever the material is on the outside, which we decided not to call it air, but at least we decided back here at surface number 1 to call it N1. So I should do that over here. And so I hope that's not confusing here if I just call that N1. So the general principle of N2 is really N1 for my problem. And of course, then we have the sine of 76 degrees. So again, so I don't confuse myself, I'm just going to cross out the basic equation of Snell's law, which just labels it in 1 and 2. As, like I said at the very beginning, calling that exit one number 2 is just a recipe for disaster. All right, but I'll stick to the notation. So here's what you know I have so far. Okay. Now, if I wonder if I should do like I did with the add 2 angles to reduce 3 to 4, or I think the math might be well, part of me wants to do it like I did the other one, but another one looks like it might be easier if I just divide the 2. I'm going to try that. I'm going to divide the 2. So it'll be a little different than I did the other ones. Let me do this. I'll write this as N1 sine of 45 degrees equals to N sine theta 3. That's that first one again. And then this one here, I'm going to just write underneath it and divide the 2 equations. But I'm going to change the order. I'm going to write N1 sine 76 degrees equals to N sine number 4. And part of this I like because the N1 cancels off. Part of it I don't like because we're trying to find the N, right? And it cancels off. However, it does allow me to find the theta 3 or theta 4. And then if I know either the theta 3, I can get the N, or the theta 4, I can get the N. So I'm just going to continue on with this. All right. So this is sine of 45 degrees in the numerator divided by sine of 70
You just froze up.
in the denominator. Crazy phone. And so what I was trying to say, but right there as it froze, was I'm I don't know if this is the most efficient way of getting there because of that extra little canceling off, which is going to make me go back a step. But watch this for a moment. Here's where, and we did this on the other problems. We made a triangle and we could do either triangle. I think in the other problems we were doing, we did this triangle, so we had to find that angle to get that angle and see how those were related. But I'm hoping this one's a little easier because if we have a rectangle with 90 degrees here, their normals would meet at 90 degrees. So I'm kind of hoping you would see that theta 3 plus theta 4 have to add up to 90 degrees. Yeah. Or maybe I could do this. This over here would be theta 4, and this over here would be theta 3. And obviously those have to add to 180. And if that's 90, those have to add to 90. So however you want to look at it, 3 and 4 have to add to 90. So if I take that back over to here and just leave sine of theta 4 down at the bottom and write this as sine of theta 3, but I'm going to write theta 3 as 90 minus theta 4. So this is 90 minus theta 4. Now, just because I get tired of writing the sine, why don't I just even calculate this if I get a number? So sine of 45 divided by sine of 76 is about a 0.7288. Okay. And then here's where I'm going to take advantage of that trig identity we did before. The sine of a plus b would be the sine of the first one times the cosine of the second plus cosine of the first sine of the second. Oh, good. This is a lot easier than the last one we did. Last time we just had general angles, but this one's a lot nicer because cosine of 90 degrees is 0. So that whole thing goes away. And last time we didn't, and we had to have the square roots of stuff. And then this is nice because sine of 90 is 1. And also, we did this last time, we took advantage of cosine being an even function. So we can just change that to a plus sign. And then if we want to simplify, cosine over a sine, and they're the same angle, theta 4, is a cotangent. Now, our calculator does not do inverse cotangents. So I need to take the reciprocal of both sides. So the reciprocal of the right-hand side is 1.3722, and the reciprocal of a cotangent is a tangent. So now I can do an inverse or arc tangent and come up with angle number 4 as 53.9. And I guess that then also means that angle number 3 is 36.7. 1. And this is the part that I wondered if I did it the long way, because now I have theta 3 and theta 4, but I still haven't found my n. And so I need to go back up to, say,
We would only need to solve one of them, right?
yeah, but I don't know n1.
Oh. Oh, can
So,
we plug it into the, oh, when we add them? My bad, sorry.
yeah, I'm not sure we can solve this for anything better than n divided by n1. Let me try. I think maybe we are going to have to assume n1 is air on the outside. So if I take this first equation and write it as sine of 45 and divide it by sine of theta 3, we get n divided by n1. So let me just calculate that one. So sine of 45 divided by sine of number 3, which we said was 36.1. And so that gives me a ratio of 1.200. But I think the other equation is going to give the same thing, right? The other equation, if I write it as n over n1, would be the sine of 76 degrees over the sine of theta 4. And that's not more information. So sine of 76 divided by the sine of number 4, which is 53.9. And again, same number, 1.22. So really all we can do is find the ratio until we assume that the outside is air. But that's going to make me look at the answers. So number 63.
Yeah, so without the assumption, that is as far as we could go with that problem, right?
I think so. Let's see. What did the author do? Yeah, see, the author right at the beginning assumed there was air on the outside. Let me read it again. Am I missing something? The light ray enters a rectangular block of plastic and emerges at an angle to it as shown in the figure. Determine the index of refraction, edge of the time. Okay. Well, this is one of those ones. And to be quite honest, that's why in the last problem, I did assume that it was in air because a lot of the problems you have to, and that's just kind of the normal, So they kind of assume it's in the air. And it turned out on the last problem, I didn't have to assume that. This one, the angles would work out as long as the ratio between the indexes was 1.22. And you can't explicitly do the plastic alone until you assume the outside is 1. All right. Well, all right. So assuming N1 is 1, then the plastic is 1.200, which is a little on the low side. I'm kind of curious, assuming. Well, assume right, isn't it? If you assume something, you make a ass out of you and me. Yeah. Okay.
Yeah.
It's a terrible way to learn how to spell it, but that's how I learned how to spell it. Okay.
Oh yeah, no, that's what I was told as a kid how to remember it.
Okay. It's got a spelling and life lesson all mixed together. All right, my crazy phone disconnected. I'll connect that one. But I am kind of curious if N1 was in water. because if I go 1.2 times 1.33, I get an N of about 1.59. And to be quite honest, I kind of like the numbers because 1.59 would be about common for a glass, a flint or a lead glass. And if it was underwater, 1.33, the numbers would make sense. I don't know what material 1.2 would be. The only thing I know that low are liquids. And so your glycol, your alcohol, your oils, and it's not easy to make a rectangular block out of a liquid. So.
Yeah, that'd be weird. It must be like super clear plastic or something they're talking about.
So, But anyways, I would feel better if this problem was really a glass block underwater. Anyways, but I digress because there's a part B to this we need to get to. All right, so the A, determine the index of refraction, and then B, if the light ray enters the plastic at the point L, 50 centimeters from this bottom edge, what time interval is required? Well, fortunately, this one's pretty straightforward, although we do need to go back to physics 121 here and say distance equals to velocity times time. And the distance, coming back to the picture here, would be along this piece here. So I'll call it D. But if you also look at this angle, how about theta 3 here, you can see that the sine of theta 3 is then this L over the D. So D would be L over sine theta 3. So giving me a number, the L, and they gave me 50 centimeters, but I'm going to just switch it to meters. So I'm going to put 0.5 for my meters. And I'm going to divide it by the sine of, and what do we say, angle 3. And angle 3 was the 36.1. So 36.1. So the light has to travel a distance of 0.849 meters. So using 0.849 meters for distance. And then the speed would be the speed of light divided by the index of the plastic, which we said was 1.2. Then I would have the T. So if I take my 3 times 10 to the 8th and divide it by 1.2, I get 2.5 times 10 to the 8th. 1, 2, 3, 4, 5, 6, 7, 8. All right, so now to get the time, I'll just go up and take that distance and divide it by that speed and copy and paste them and come up with 3.39. And that looks like that's in nanoseconds times 10 to the minus 9. So a little over 3 nanoseconds. We'll kind of race through there. Nice. Yay.
Thank you.
Nice.
Also, one cool thing, I don't know if you might want to check it out, but they on YouTube, they actually they have a video where they actually are able, they have a camera that goes so slow that they can actually capture light moving through an object.
Yeah. Oh, yeah. These femto frames. Femto is 10 to the minus 15th of a second. Yeah.
Mm-hmm.
Yeah.
Yeah, I saw it the other day, and that blew my mind. That was so cool.
Yeah, yeah, that blows my mind. Yeah, that's not that old. I mean, that's, they've been working on femto lasers and femto frames with the idea that if you could get it, you could actually start seeing chemical reactions in progress. You can see, okay, it does this, then it twists this way. And yeah, so in the last 10 years, they're finally getting to that. I mean, it's still a developing technology and a developing art, but just to be able to see, light as it moves through. Yeah, I've seen these pulses. Yeah, that's another thing, is just making a pulse that is time-wise short enough, because it travels so fast. If you want to see it move, you got to make it short. So you got to make a femto pulse and then be able to see it in a femto frame. It's just amazing they can even,
Yeah.
And and they've been totally trying to do that to get things like, why, to actually see the mechanism. And we know that, say, this is probably over too simple, but we know that when you burn hydrogen, it mixes with the oxygen. But it's, how it bonds, how it twists, how it rotates, and particularly the bigger proteins, especially when it comes to human diseases. And, I mean, can you imagine if you had a video of how the coronavirus actually attached to the cell? I mean, what kind of information would that give you on how to then stop the coronavirus from attaching to the cell? And you see it maybe in and do a left twist, inner angle, pull in, whatever that mechanism is, you might be able to come up with some kind of way of stopping it, just because you actually could see that it twisted left instead of right, or moved forward twice and stopped twice,
Yeah.
Crazy. So
It'd be super cool seeing also how like something actually combusts, like seeing a flame being developed like on the sun or something too.
Yeah. Yeah. And of course, in terms of technology, without seeing the individual molecules, we've been having cameras pretty good at that. And so that's made a huge difference in fuel economies. They actually burn the fuel and watch how the flame moves out, and then knowing then how best to make your spark plug, where to inject your spark plug. And so, yeah, just knowing the whole kinematics of a burning flame has really helped. And that has only come around when cameras got, fast enough. Those are nano cameras, not femto cameras, but nano cameras are still, billion frames in a second. I mean, come on.
Yeah.
How long does that take to download? If you took 1 second of video, you now have a billion frames. And if each frame is, let's say you take a picture that's 10 megabytes, well, not even that, just 4 megabytes. 4 million.
Yeah, it's a bunch of gigabytes.
Times 1 giga. That's 4 times 10 to the 15. So that's 1,000 terabytes. I think I'm happy with my 4 terabyte hard drive. So I guess I'd need 250 of my 4 terabyte hard drive just to download a 1 second video from this nano camera, let alone a femto camera. So obviously, you don't take a picture of it for 1 second. You take a picture for a nanosecond.
Yeah, it's crazy. I didn't actually think about the data of that.
Too much data.
Yeah. Awesome. Well, I think I'm gonna head out. Thanks for the talk. Good, always good.
Right.
Thanks for the help too.
All right, guys. We will keep talking, keep working.
Thank you for the help today.
You're welcome.
Bye.
Bye now.